Today we'll be hosting Dr. Kemal Akoğlu. He's actually one of the hosts as well. He's from the Faculty of Education from Boğaziçi University. He'll be delivering his talk titled Probability, the Mathematics of Uncertainty. I'm quite certain that it's going to be a stimulating talk. We'll have approximately 40 minutes for Dr. Akoğlu, and then we'll have a Q&A session afterwards. Okay, I'll leave the floor to you. Thank you.
Good afternoon, everyone. It's great to see you here. Welcome to my talk. So let me go and share my screen right away with you. I am Kemal Akoğlu, as Dr. Engin Ader presented. I am a faculty in Mathematics and Science Education department in Boğaziçi University. I graduated from Ankara University Mathematics Department in 2018, and in 2014 I got my master's degree in Mathematics Education at North Carolina State University. My master's research subject was research-based suggestions to overcome the cognitive issues in teaching and learning of conditional probability. And then, without a leave of absence, I continued pursuing my PhD study at NC State University. Under the direction of Dr. Hollerenli, I prepared my dissertation and defended on December 2017, sorry. And that dissertation was again focused on developing teaching statistics practices. So then in 2019, I started to teach as a part-time instructor at Boğaziçi University, and 2020 was the year I started my full-time faculty position here. So let's start then. So, Probability as a Stranger in the Town was the first title of my slides. The reason I got this title was because of its unmathematicality of it. When it comes to mathematics, we simply, I mean, according to a strong theory, mathematics was invented to simplify the complex universe around us, to make it meaningful for us. I mean, there was this day, night, there were lots of observations where it was not that easy to understand that world, and probably human cognition was not fitting to that complexity of things. So we created a language of the nature to make it possible to be simplified. Then this language was mainly based on the determinism and certainty. So there was a relationship between a cause and the effect of it. And the results out of this language, this set of formulations and set of syntaxes, like in a language, had to be certain, concrete. So probability was not a good fit to this discipline. The way we looked at uncertain events, uncertainty was based on our beliefs about the universe as an authoritarian rule maker. So there was a cause, even though we do not know it. So there was no way or no reason to question it. Destiny was very, let's say, popular among philosophers and all human beings, actually, especially because of the medieval age, which lasted probably more than 1,000 years, where, especially in Europe, the power of church was so strong. So it was not okay to question the unquestionable, which is the future, the unknown, okay? So the concepts of chance and randomness were like, not maybe sin, but they were not okay to be mentioned. Mathematicians, one, because of this, probably the strength of the church religion, and second, because of the overwhelming role of determinism and certainty in mathematics, they did not they did not mention a mathematics of probabilistic events or a mathematics of random events. But there was something going on, and that was probably as old as the human civilization, and that was gambling. People gambled since the time we are able to have some records about their everyday lives. They use those heel bones of deers and sheep called astragalus. The astragalus was the probably first primal die they used for gambling, and it did not have equal probabilities for every side of it. But we have evidence that this heel bone was used to gamble. So gambling was so old and so popular among people that probably that popularity emerged the birth of probability as a discipline, as we will see. But what were they doing to understand, to make decisions, actually, as we will relate to everything we talked about here? They were using proof of witnesses, as it is something we use now today, and proof of the authority. So an authoritarian, a virtuous other, was a good evidence to make a decision. Then the thing's interior proof took place before the Renaissance, and at that time, instead of the proof of authority, science started to be used. Experimental method was a very new and strong subject among the thinkers, the thinker humans, let's say. But there was still too many things to overcome first to reach that point where we can use probability for our scientific works. So testing, either approving or denying a hypothesis by just showing was the case. Then there was something Jan Hacking calls it as adventure. So suggesting a theory with no strong evidence. I mean, a man in Greek said that the world is flat, and he attempted to construct his adventurous theory based on just first, with no evidence assumption. Diagnosis was the thing, actually, a very essential component of scientific work. It was showing one thing as evidence of something else, and the birth of diagnosis as a stakeholder, let's say, was happening in the Renaissance. What was Renaissance? Renaissance started to be effective among the artists first, and the thing done was to take this bond to religion and make the art more humanitarian. So, as you know, I mean, the paintings of Jesus before Renaissance was not reflecting a human baby at all. It was just perfect, but we saw the first normal baby pictures or paintings during the Renaissance. And also in the scientific works of things, it was not necessary to conceptualize the inner proof of things before the experimental method took place. So the emergence of diagnosis in the 17th century, when the experimental method of reasoning was glorified, was a very important phase to understand and to mention for understanding the birth of probability. So experimentation and reasoning to explain how Renaissance and Enlightenment period affected the scientific fields is important. So something smaller, inner, atomic, and precise was inferred from something much larger, outer, rough, and imprecise. An attempt was made to read the state of the atomic world from the raw diagnostic tools at hand, just as the doctor reads the patient's condition from the urine symptom and decides on a diagnosis at the time. So scientia, the old science, was looking at the results as the result is decided as seeing it in the way of passing a test was to pass a test. New science was telling us that the new philosophy of inductive reasoning, and in that the result of passing a test was just to obtain new inductive evidence for a hypothesis. So things just changed their steps in that. The term probable was not used in the books, in the works of mathematicians at all until 17th century. As I said,
Kemal Hocam,
yes.
Is it possible you have a microphone handy just to increase the quality of the sound a tiny bit? Thank you.
Is it better now?
Maybe a bit better. Thank you.
Okay. So the old analytical truth was telling us that what is needed to transcribe the possible is to reproduce the works of others. Okay. So anyone who makes a great effort to a possible idea, not probable, was necessarily just an imitator or an interpreter. At the time, we had Paracelsus, who made a revolution in the field of medicine at the time. We had Copernicus, who is known with the Copernican revolution, which refers to changing a notion or a belief which was the case for thousands of years, and that was the world is in the center of universe. So Copernicus said it is probably not, and it is probably not only that, but the Earth is not in the center of universe. The Earth is just orbiting a star, and that star also is not in the center of the universe, probably. So the way Copernicus changed the uniqueness of the Earth in the universe influenced or inspired philosophers or mathematicians. From philosophers, we will talk about Vico, Giambattista Vico, the Italian philosophers, who is considered as the father of social sciences to some extent, and Immanuel Kant, who actually made the way we see the knowledge, the truth, radically different from the way we saw it before him. So truth or knowledge was seen as an objective thing. It is something out there, and we could try to reach it. Okay? Kant said it doesn't have to be like that. Maybe like Copernicus' approach, maybe the knowledge was not in the center of the knowing process. Instead, the knower is. So the knower constructs the knowledge. Okay? So, and he used the quote, sapere aude, dare to know. And according to his approach, his epistemological approach, there was too much openness for constructing new knowledge and to progress as the novel. So the revolt against the futile repetition was in the center of Enlightenment period. Enlightenment period was not only about Kant and Vico, of course. René Descartes had put the human reason to the center of understanding the nature. And he said, a larger problem, a greater problem could be understood by taking it into the pieces and first understand those pieces, okay? So that deductive reasoning was a radical effort to make the logic more in action, actually. The testimony coupled with frequency, that was the old notion of probability. Here, stable and law-like regularities become both observable and worth to observe. In this way, a part of the technique of reading the real world was formed, and the proposition was only possible if it had an evidence, not if it is approved by the virtuous or righteous or a script. So the concept of sign was probably the strongest indicator which gave us the first probabilistic approach. So the probability has emerged for the first time and in all aspects except its name before 17th century, but very close to that time. Being aware of the new internal evidence and frequency, those meet hand in hand in the same glow, leading to a single concept, which was called the sign. Tom Hobbes, in his book Human Nature, said, although one has always seen that day and night follow each other by now, he still cannot, by looking at it, conclude that it is experience does not give universal result of anything. If the science hits 20 times and one misses, one bet could be made on the event, but still no truth can be deduced from this. There was no term of probability, and it was 1640, and after that, the actual story began. A very rich and a mathematical enthusiast gambler named Chevalier de Mer approached, according to a story, they met in a trip. So approached to Blaise Pascal and asked him whether it is possible to answer this problematic situation. In a dice game, if the game is stopped before the end of the game, is it fair? It is fair how the money in the hand and the table is divided up. So what was the solution to this problem? If the game was stopped suddenly by the game host, what was the fair way to divide the accumulated money or whatever it was? And Blaise Pascal, who was one of the greatest mathematicians ever lived, was not able to answer that question first, okay? And he wrote a letter to Pierre de Fermat, another mathematician, another great mathematician, luckily living at the same time in France. And they started a letter correspondence, and that letter correspondence lasted for 6 years. After those 6 years, we had the first probability theory, where we could actually explain sample space and how the ratio of the event to sample space was giving us a clue about our decision-making processes. The modern probability theory waited until 1933, when Russian mathematician Kolmogorov constructed the first axiomatic system using the sample space. So there were two things important to understand those attempts. So we were talking about one expectation, and that was from a coincidental or random point of view. This term was the average return on similar games over the long run. The total was converted into an average gain sum, and the expectation could be observed more readily than probability. Probability was different from that. So we had this distinction between both at the time. The likelihood or non-occurrence of an event was a judgment we make about the event by comparing the number of chances of its happening with the number of chances of it not happening. That is the way we could call something likely or not likely, probable or improbable. Another great mathematician at the time, again, Leibniz, I like this quote, so I wanted to share it, and that was before probably first systematic probability theory was formed. Leibniz is very well known about his contributions to derivation, integrals, but he also taught a lot about the concept of probability without using it. So if one can have a basic alphabet of human thought, any complex idea can be formed from combinations of these alphabet elements. All possible ideas and all possible propositions could be created mechanically so that we could not only investigate what we know, but also investigate what we do not know, and thereby make deeper investigations. And to follow this thought, we could support our decisions based on those deeper investigations. So we could make better decisions, more reasonable decisions with the popular word at the time. Then we have Laplace, again another great mathematician, who gave us another version of understanding of probability. So he said, actually, there is no probability at all. Okay, there are no equal probabilities. This is only a measurement of our ignorances. We say that in a coin toss experiment, head and tail have equal probabilities because our ignorance about the result is equally distributed to both outcomes. Otherwise, I mean, how can we make sure about the air pressure, the interior elements of that coin, the force we give to that coin toss? And he said, since the world is determined, so that was always the base assumption. Since the world is determined, there is actually no possibility in things. Probabilities arise from our ignorance. In fact, our situation is this. The theory of chance consists of reducing all events appearing at the same time to a certain number of equally probable events. That is, events such that we are equally undecided about their happening. And Laplace's demon gives us a scary scenario. So he says, because everything is determined, because everything somehow, either we know or don't know, has some algorithms to happen, if we have the way to calculate all those mechanisms of the nature, and that is called Laplace's demon. So a being, not a human probably, if calculates all those stuff, he or she could know, or it could know everything to happen. And he attempted to prove that mathematically. So another good story. So in 1800s, in 19th century, there was this great experience, a historical experience, let's say. This is a heading from the newspaper, from the French newspaper called L'Aurora, and J'accuse, I blame. It was written by the great author, novelist Emile Zola. So this guy, Alfred Dreyfus, was a major in the French army, and in the German ambassador building, there was this fire, okay? After the fire, an espionage letter was found in that building. So Major Dreyfus and around 10 other generals from French army were known as intruders to this building at that time. Because of the generals' titles, the Judiciary Committee decided to only question Alfred Dreyfus, and the way they figured that Dreyfus was to blame, was guilty, was just making him to write something with his handwriting and compare his handwriting to the letter found in the building. And they said they are very much alike, so Alfred Dreyfus is guilty, and they sent him to an island as a prisoner. Emile Zola was so frustrated because of this, according to him, unjust decision, and he wrote this letter. This guy in the middle, this is Emile Zola. The guy in the middle is again another great mathematician from history, Henry Poincaré. Henry Poincaré read that article, and he voluntarily asked to the Judiciary Committee to involve as a scientific observer. And he, with a group of mathematicians, after 4 years of deep investigation, he proved that it was not enough to state that Alfred Dreyfus was the writer of that letter just by comparing those two letters. The allegory he used, he said, if you toss a coin 10 times in a row and you get heads 10 times in a row, it could be something to believe, okay? It could be due to chance. But if you repeat that experiment many times, and if it is still like that, then you can have a clue, but still uncertain. You would be uncertain about the result. And he said, just going with this comparison of these two letters, you cannot approach that. And he proved that mathematically, and Alfred Dreyfus was rescued. And Emile Zola wrote a book about that Dreyfus event. It's a great book if you are interested. So what is the problem about probability? Let's come to the notion of probability as we know it right now. It is difficult, not only because it's contextual or contextual nature, but it is difficult for learning and teaching because there have been very strong and very resistant misconceptions about probability. Those misconceptions are about the concepts, about the random phenomena. It is not easy to understand. I saw lots of students telling me that the event I call random would not be random because of blah and blah. And there are really convincing argumentations about those. So it is not that easy to define randomness. So think about the random number generator. So a computer program has a back algorithm or a seed value for a graphing calculator, and that decides to the result, okay? There is an algorithm behind that. So the number generated from that random number generator, actually not random, we call it pseudo-random. What about in these physical experiments? I mean, as I said, there is this air pressure, the force, the elements in that coin, and if you could measure all those physical factors, you could know the result. You could know the result. So what is random about it? I heard that question a lot. So it takes us back to Laplace's approach. It's just our ignorance, probably. Then the concept of chance, the concept of availability, the concept of representativeness. I mean, how could a model represent a larger thought, a larger concept? The concept of outcome is another problem, a big misconception. For example, I know a very good mathematician, and she has been studying math for more than 20 years, and still she tells me that getting a 2 from a die experiment, rolling a die experiment, is 50%. And I asked why, and she says, because either it will happen or not. At the end, I will observe or not observe this outcome. So that is what how I reason about this situation. That is really difficult to overcome. Another one, I know a guy, my father actually, he has been playing lottery, sayısal lotto, for over 25 years. And he has been playing for the same 6 number for every single week. And he records every single week's results. And I asked him, why are you doing that? He said, if it is not loaded, if it is a fair lottery, sooner or later, those 6 numbers will win. And that is called the gambler's fallacy, or in other words, and is convinced. So in other words, it's called the negative recency effect, not understanding the independence of events. But it is difficult to overcome. Students, so we ask students the question, first we teach them that getting 10 heads in a row of 10 toss coin experiments, coin toss experiments, is 1/2 powered by 10. And then we ask them this question. What about this? I tossed the coin for 9 times and I got heads. Now I am going to toss the coin for the 10th time. And would you bet on head or tail? And he says, or she says, tail. Why? Because getting heads 10 times in a row is 1/2 powered by 10, which is 1,024. And that makes not getting 10 heads in a row 1,023 over 1,024, which is very high, a very high probability. So why wouldn't I bet for that? And then as a teacher, you laugh at the student and tell him or her that, but these events are independent. The 10th toss is independent from 9 previous ones. So you are wrong. They still have equal chances. Then the student asks this. Then why did you teach me the previous information? Why do I know that? Getting 10 heads in a row is 1/2 powered by 10. So in this event as a whole, in this experiment as a whole, I can stop my approach to the experiment. And I can say that, you know what, these 3, in my reasoning about 10 heads in a row, I can go to the 5th toss, and I can say that, you know what, at that point, those 4 are already happened. And you have a good answer for that. So why would I approach an experiment in terms of their compoundness? So that is a problem. That is not easy to understand. So is it useful for me or not? Well, it has to satisfy their common sense, and that is not that easy. then we have fault paradox or a time axis fallacy. So we say that there are two conditional events, and the early event could affect the later event. All right, then we talk about Bayes theorem, and we say that when we make inferences, okay, when we try to make predictions, knowing I mean, instead of getting the future dependent on the past, we could talk about the past depending on future. That is not easy to understand. I know that I will get this in my second pick of balls from that urn. So what is the probability of getting that in my first pick? That is not easy to understand. And there are very strong misconceptions about those. Actually, there is a work by Fishbein and Schnarr in 1997 talking about the evolution of misconceptions, the probabilistic misconceptions by age and education, and that found that all those misconceptions increase by time and by learning about probability. So whatever we are doing to teach probability, not only insufficient, but probably wrong and harmful. And what causes those? The wording we use in process of teaching and assessing the topic. So when we use the words as random, likely, confident, we should be very sensitive, especially math teachers, of course. Interference from causal reasoning. Believe that causal relationships should be stronger than diagnostic ones. So correlation does not imply causation. This is a very well-known quote. Contextual knowledge that implies a causal relationship for the events and the syntax involved in answering the question, and the distinction between dependent and independent events, whether events can really be independent. So we should focus our teaching strategies to those. I talked about Fishbein and Schnarr. So we talked about the examples of common and resistant misconceptions in probability. This is, again, I mean, Fishbein attempted to use experimental activities involving probability generators to transform children's primary intuitions about probability into restructured cognitive beliefs or secondary intuitions. And as I said, the misconceptions, according to that study about probability, were increasing by age and education. So a new tool is very vital for us to overcome those problems. Computers, technological environments, they provide powerful classroom environments for creating more realistic simulations and for generating data. Teachers need to produce probabilistic tasks are linked to teaching objectives and are also engaging for learners using technological tools. So, Jan Hacking, the author of this book, which is, I don't know if you are seeing it, Olasılığın Doğuşu, The Emergence of Probability by Jan Hacking. It's just published, and it's a great book. He says probability, let's say, arose from the Renaissance. This is sufficient for an analytical problem about induction. The skeptical problem could arise only when causality moves from knowledge to idea. Okay? So we don't have to go and find that hidden truth somewhere. Okay? We could have a sense, an idea. We can make predictions for our decisions, for our beliefs. Okay? We can update our beliefs according to new evidences found. The emergence of probability and induction is a more complete event linked to parallel transformations in various kinds of scientific fields. So here comes statistics. Statistics is an important product of this newcomer to the town. Data, what we call data, is everywhere in all sorts of ways. It is so complex and too much, and it always increases and becomes more effective and fringe. Think about the COVID-19 process. I mean, the data is accumulated every single day, and we are trying to deal with it. Dealing with data is a very essential task of today's researcher. So we make descriptions based on data, we make inferences on data, and we use that in all fields of science, medicine, economics, engineering, politics. We have to do that. We have to do that because this data, this huge data, could just defeat us. Okay, just think about the recent experience we have been having with COVID-19. So as an epilogue, human, despite her or his ignorance, is a creature that has to make decisions in the grip of uncertainties in order to survive. That is how we came this far, okay? We make decisions in our individual lives or in our societal lives. And that human is unable to find a way to deal with that ignorance about the unknown or about the uncertain. So he constantly makes decisions based on approximate results using the data. And sometimes she or he is wrong, sometimes she or he is not wrong. So not only in scientific work, it is the same in our everyday life. So as the last word, knowing statistics really helps us to move on. And that is the whole story from my end. Thank you so much for listening. I would be happy to answer your questions if there is any.
Thank you so much, Kemal Hocam, for this inspiring talk about the historical roots, the conceptual developments, and potential manifestations of these ideas, possibly in flawed ways. I see a hand up already, Tülay Ayıldız, starting the discussion.
First, thank you for the great talk because you made the subject very approachable. But I have some comments. First one is about your first slide. You told us statistics or probability gives us a meaning of the universe, which is a really big word and unfortunately is not true because we have used the data. And in the modern world, thanks to Google, we have plenty of that. And we just get a really small part of the data and just trying to make sense of it. So it cannot really give the meaning of the universe, but it can just give us a sense on a really small subject. And my another comment, as a mathematician, I think I need to defend mathematics a little bit. Okay. I don't think they are that diverse. I don't think math or probability is not that unmathematical. Because the structure of probability, how we study, is topological, right? The probability is a topological structure. It has the measure between 0 and 1. So we cannot really understand or use probability without mathematics.
Of course.
Also, in the really modern world, again, like you gave the example of COVID and stuff, they make the models, mathematical models, to predict how it's going to spread or how vaccination could be done, right? They use lots of mathematical models, and those models are mathematical, and they use statistical parameters to make this stuff work. On the other hand, did it work? Usually not. Okay, we failed as the whole scientific world in COVID really badly. I can blame statistics more than mathematics in that failure.
Okay, that would be a big fight. Thank you. Is that it?
Yeah, thank you.
Thank you so much. So firstly, I don't know if I said statistics and probability is trying to give the meaning of world. I said it assists that
It is on your very first slide. You can check
Okay. You're right. I mean, the title of the whole discussion was the mathematics of uncertainty. So whatever claims we do in this sense should be uncertain at the end. I'll look at it. So, yeah, the nature of mathematics, I said, simplifying the complexity of universe to make it meaningful. That was what I said, actually. So it was about mathematics, not statistics. Here it is. So I said the nature of mathematics. I mean, what we attempt to do as human beings since the beginning of the invention of mathematics is to simplify the complexity of universe and to make it meaningful. And by meaningful, I mean to survive with this complexity, actually. So probably, again, these wording or concepts we use here are, again, problematic. But I use that for mathematics first. For the later comment, I mean, I came from mathematics as well, but what I think is not set, what I defend is not to say that mathematics and statistics are totally different. They should be taught separately to me. I mean, statistics is kind of, it's contextual. In mathematics, maybe in modeling, yes, but in mathematics, we do not need context that much. In statistics, that is all what we need to me. I mean, we always are dealing with the context in statistics. So, especially in teaching and learning of probability and statistics, the differentiation between them, I think, is important. But in a higher science level, it is debatable. I don't know. I mean, I should know more pure mathematics, maybe, or more modern mathematics to make that kind of claim. But thank you for your question and comment.
Thank you for answering.
Any other question? Okay.
Thank you so much for the great talk, Kemal. It was really, I mean, it's always, you know, I feel like thrilled when listening to your ideas. That was really good. Thank you. My question is actually, it goes back to Tilay's question also. You said that you are kind of like making the point, the difference between probability statistics and mathematics in terms of learning and teaching, rather than, you know, as two disciplines of science, let's say. But it makes me think about, like, and also the you know, the teaching and learning of probability mostly focuses on students' misconceptions or overcoming those, you know, maybe some specific ideas, independent dependent events, blah blah, right? But like with also Tilay's comments, is there any research or I don't know how to say this, like I wonder your ideas actually, even if there is no research, that uncertainty as something to measure, right? I mean, because we are talking about 0 and 1, topology of 0 and 1, she said, right? In topology, we have this measure of 0, 1, right? So just one unit. And then we are mentioning measure of something, and measure of something is uncertainty. You have been talking all about uncertainty, right? So thinking about uncertainty as something to measure, like, what do you think about it? Like, how we can, I don't know, like, even like thinking about it something to measure is really hard for the adults, but also we are talking about learners, right? So is there any research on it, like, or what do you think about it? Like, how can we overcome that, or maybe just, help students think about it as a measure?
So probably, thank you so much, Ms. Ranjan. Is that it? Can I answer? Okay. So I think the question you asked is twofold. First is still digging this mathematics and statistics differences. I think there is a big issue about that, and this is really very debatable. Here is the thing. From a mathematics point of view, okay, I don't know what mathematicians think, but we try to get that point of certainty, okay? We have to do that. 2 times 2 should be 4 in every single universe, right? When you try to measure this uncertainty, and let's add variability to it, okay? I mean, you get into that chaos, okay? You get into that adventurous theoretician's state. I mean, at a certain point, this is my idea, okay? And a little bit maybe other researchers' idea, but at a certain point, you should make a strong assumption. And when you get those assumptions in play, okay, and use them as measured values, where actually there is no something really measured, okay, I think that action itself is making an assumption for a certain goal. Second, and this is very debatable, as I said. I mean, there is a huge discussion about that. But the second part of your question about teaching and learning of probability, I think one of the biggest problems about the teaching and learning of probability is the time we begin teaching it. That is all about Piaget's approach when he said the possibility of understanding this concept of chance is only possible when you have this combinatorial and proportional reasoning. And that is formed in formal operational stage, which is 12 to 14 and above, age 12 to 14 and above. And we started to teach probability at 7th grade. In all of the curriculums, it was like that. But now it changed. It changed. I mean, the probability concept inventories are not that much. So we really just stick to Piaget's and Inhelder's idea about it. That was not experimented. I mean, it is a huge thing to say that the concept of likeliness or the concept of chance cannot be formed before age 12. So I think this is a very important phase to start teaching probability at a much earlier age, okay? And also, of course, using the computer technologies to make those experiments more observable for students, where they can see a large data in play. Thank you for your question. I hope it answered a little bit. I don't know. I mean, maybe I made some more confusions. Yeah. Yeah, of course. Any other question?
An afternoon of hard questions. Let's see if we have some other questions or reactions to the talk.
For those who are interested, I want to show the book again. So this is a great book by Jan Hacking, and it helped me a lot to understand the story of the birth of probability while I was preparing my master's thesis. So it's just translated to Turkish, and it's really helpful. I want to make an additional comment, if it's okay. So I teach teaching and learning of teaching statistics and probability class at Boğaziçi University. This is my second year teaching it. And in the beginning of every class, I ask students whether about their feelings about probability, about the subject of probability. And mostly I get 95%, maybe 98% of the students saying that either they are scared of probability, or they hate probability, or they don't understand probability. And those are junior students of Boğaziçi University Mathematics Education Department. So, and I tell them about my experience, how I feel about probability. Let me share that. I mean, since I started to work on this issue, and it has been 10 years, 11 years, I fell in love with the subject, because every single day I feel the relevance of the subject to me as a cognitive human being, and to the world around me. So I really believe that dealing with probability and statistics would not only help us to move on, but would heal us somehow. I think someone wants to ask a question, by the way. Okay.
Yes, Okan Altılar.
Yes.
I think there is a question from him. Would you like to pose your question, or?
Hey, hello.
Okay. Yeah, we can hear you.
Can you hear me?
Yes.
Sure.
Hi, Kemal. How are you?
Hi, good. I'm
Long time.
Yes, long time no see.
Thanks for the conversation.
Thank you so much.
I want to ask a question. I'm not mathematician, but in computer simulations, when you want a random number, you always have a seed. Computers have a seed.
Yes.
And when we talk about randomness, we always talk about one seed that the random numbers takes the reference. Now,
Yes.
I don't know if I can tell very well.
Yes.
So this can be a random, this can be a number, any seed, but this is called pseudo-randomness, not real randomness.
Yes,
So
of course.
it's right, yeah. But when the computer wants real randomness, it uses like mouse movements, coordinates, because they are random movements. We move the mouse or the keyboards, or random acts in the life. Computer collect this data and then use it like a real random process for using in a real random process. So before the computer, how the mathematicians were dealing with this problem, creating something random before I really don't know and want to know how they were dealing with this problem. And is it possible in nature? Is there a seed in nature? Is there a real seed? If the life is a simulation, some people think about this, and it's a strong theory today. So if life is a simulation, what could be this seed? What can be this seed?
Okay, thank you for the question, Okan. This is a very difficult question. First, if we think like Laplace, okay, of course there is a seed, okay, and the only reason we call events random is due to our ignorance, okay, the level of our ignorance. On the other hand, the way we were presenting random situations was through modeling approach. So we were using different methods, like a Monte Carlo method. So we were taking let's say, die rolling a die and roll it to represent some problem context. Okay, and we were dealing with that with hands-on activities, actually. So that was quite hard to deal with the misconceptions we listed in the presentation with that way. So it is a great point. This is why it is now possible to dive into the problem of understanding probability, because we have all these technological materials, tools. So it has been a popular subject to research for around 20 years, only that. And before that, it was just mostly in that theoretical phase. So now we can make all those connections, and we can talk about the term big data or data science. Before that, it was impossible. You are right about your observation. Thank you.
Okay, thank you to you.
One more question. Okay, Tülay.
I actually want to make a comment about his question. The problem of the one seat, the computer has just one seat, okay? But in the real life, our timeline is continuous. And the other model stuff, or most of the nature of probability is discrete. The connection between discreteness and continuity is a big problem that we cannot really imitate the real life randomness. That is one of the points. The continuity in real life and our mortal lives, or mortalness, makes everything hard to understand.
I mean, maybe this data science efforts could help us to deal with that in that term. I don't know.
Yeah, there are models. The models are all look like a tree diagrams, and at the beginning of each branch, seed changes. But in real life, that branches are so close to each other, and they are continuous at the end. So we kind of imitate that with the networks and tree diagrams, but we are not close to the real randomness.
Thank you.
One more question coming. Burhan Bey.
Hello, everyone. My name is Burhan. I am a friend of Kemal. How are you, Kemal?
Thank you. I'm fine. I hope you are fine.
Thank you for your presentation. And I want to raise a question. Maybe I missed it, but my question is about the relation of the realm of probability and the observation. I mean, in physics, as all you know about Schrödinger's experiment, the observer affects the outcome.
Yes.
So when you put probability, how mathematicians take the issue, the relation between the realm of probability and the observation, the effect of observer. I mean, thank you.
Thank you so much for the question, Burhan. Yeah, in the presentation, because we had this limited time, I didn't talk about the theoretical probability, frequentist probability, and subjective probability. So yes, when we talk about probability, we have different approaches to it. So classical probability is about the theoretical fundamentals of probability, but also we are dealing with frequentist probability, where all we do is observe the frequencies of an experiment. So probably in sciences like physics or engineering, this is the way we should approach. I mean, the classical probability is just maybe a reference point for that observed frequentist outcome of probabilities. Let's say, but other than that, again, the role of observer, that is another discussion point. I think I should think about it. Thank you so much, Burhan.
Thank you, Kemal.
Okay, we're actually 10 minutes into the 15th hour of the day. So I'm just looking for one final question, if there's any hands up. If not, maybe it's a good time to conclude the session and the discussion. Thank you very much, Kemal Hocam, for your talk and contributions.
Thank you very much for hosting me, and thank you to everyone for being here and being patient to listen to the talk.
We'll have our next seminar in 2 weeks' time by Gaye Ceyhan, and we hope to see you all here again.
Thank you. Have a great day.
Thank you.
Thank you, Kemal Hocam.